everyone, this is Sarah DeMeo with Acuity Solutions, and welcome to part 2 of our 5-part webinar series, How to Expand Your Business with NX for Manufacturing. We put this series together because today's manufacturing climate is changing rapidly, and companies like yours are investing in advanced multi-axis, multi-function machine tools to handle this changing environment. I would bet that if you're watching this today, you are likely experiencing at least one of the following challenges. Your products may be more complex, whether in shape, structure, or size. Many of you are dealing with increasingly shorter lead times and delivery requirements. You may even suffer a penalty for being behind schedule. You might be a design company who has decided to bring your prototype manufacturing in-house. You could be a job shop who specializes in short-run production, which means you need to be able to program your parts quickly to maximize your profit. If you don't identify with at least one of the above, I can almost guarantee that your company uses multiple software packages to solve your different manufacturing problems. These programs likely don't talk to each other and can greatly reduce your efficiency. In today's session, we're going to cover NX Integrated Simulation and Verification, or IS&V. NX IS&V is fully integrated into the familiar NX CAD and CAM programming environment, allowing you to visualize the entire process from 3D model to finished part in your common 3D environment. Its real-time G-code monitoring allows for on-the-fly error and collision detection, allowing you to quickly correct your problems. Finally, it may help you to eliminate the need for another system like Vericut, potentially reducing your costly maintenance fees. Now I'll hand it over to Andy Schaefers for the in-depth demonstration. Thanks, Andy.
Thanks, Sarah. Can you see my screen here?
I can.
Okay. Let's get started then with the review of the IS&V options in NX CAM. If you're familiar with NX CAM already, you'll recognize the operation navigator with our pockets and our tools here. What's different is up at the top it says 3-axis mill vertical, and that represents the machine tool that I brought in. Let's look at some of the options that are available to us here with this machine tool. I'm going to bring up my axis positions, and from here, if I just move the levers on each axis, I can see the full range of motion that's available to me with any of those axes. This is useful for determining whether or not a particular fixture or part is going to fit on a machine tool, and you'll have enough travel to reach all areas of the part required, and you can quickly select a different machine tool if that's not going to work. That makes things quicker and more efficient for you. Once you've got a program created, though, we're going to actually want to simulate that program. Because of our capabilities with the simulation machines, we're able to accurately simulate all motion of your machine tool, including the tool changer as we see here. Let's go through this now. I'm back at the Operation Navigator in the Program view, and I'll start with the top level program. All you do is right-click and choose Simulate. It gave me a little warning there about a spindle speed in one of the operations that was 0. That's a nice feature that lets you know whether you've got a valid program or not, and you can fix it quickly before sending it to the shop floor. Okay, this is our simulation control panel. There's a lot of information and options available here. We'll go through as many as we have time for. I have 2 different modes that I can visualize in. First, the toolpath simulate is not the full simulation of your machine tool. All it does is look at the tool path for a given operation and run the tool through it. So you won't actually see the tool changes and things like that. The machine code simulation is our most comprehensive simulation type. In this visualization mode, we are looking at the velocities and accelerations of the axis of the physical machine tool, so we're going to get a very accurate calculation of the time required to complete the cycle. The way it works is the operations are fed to the post processor for your machine tool in the background, and that G-code's read into a buffer. then the contents of the buffer are read into the simulation engine, and that's what generates the motion. I'll step through this, which really is just like single block on your machine tool, and you see the G-code appear in the window. As soon as we start getting to some motion, here you see the code appear. I'm going to turn on 3D material removal, which creates a solid block here. At this point, then, you can see the meaning of the coordinate system. This is our G54, and we've also got a G53 coordinate system up here. So now we're actually machining the part, and because it's a dynamic view, I can rotate while the simulation is taking place. So here the material is being removed. We'll be looking at several things, the remaining material, but we'll also be looking at any errors that I made in programming. So it's nice to pick up the collisions, but there's other programming problems that we'd like to fix, like you see the extra material that's being left there on the corner. That's something that we probably want to straighten out. Okay, there was a tool change. I'm going to turn off the display of the toolpath and make it a little easier to see what's going on here. And right now it looks like I've got another problem. I'm doing some air cutting. Now finally it's starting to machine again. You can see we've changed color so that the current tool is being shown in green. That makes it easier to see which features are being machined with the tool that's currently in process. So I've got another problem there, or maybe I'm going a little bit thick on that. That's maybe a third thing I'd want to fix. And at this point I'll speed this up so we get through it a little faster. So I'm just using my toolbar here to speed up or slow down as required. There's the slot, and I am going to slow down. You see it actually making the tool change here, moving the axis in and out. And this is very helpful when you're trying to really optimize your cycle time, and you need to be able to see which tool positions are going to give you the fastest tool changes. Okay, here we're just drilling a couple of holes. Here's our last tool change. And now we're just circular interpolating those holes. Okay, we've put the tool back in the spindle, and if we look back up here, we can see now the coolant is turned off. Our last spindle speed is here, and this is the total cycle time to create that part. If we like that program, we'd hit the G-code button right here, and it would save this current NC program so we could send this to the machine tool. And this way, then, you guarantee that the code you just simulated is the code you're sending out to the shop floor. We can now look at several other options that are available. I'd like to show thickness by color. It's going to take it just a second to compute this, but it's looking at our part against the original model and giving us a gradient display of the remaining material. So if I move out here into the graphics window and click, it tells me that I've got a distance of about 1 millimeter, which is correct. And on this, it's 0, which is also correct because I'd run that to finish. So in this way, then, you can quickly figure out if you've got a problem where you've gone too deep, or if you've got additional operations that were neglected and need to be added to your program. Going back to the simulation control panel, though, as I mentioned, in this case, we read the G-code into a buffer from the actual operations in NX. There are other situations, though, where we want to interact with G-code. For instance, what if someone made some hand edits to a program out on the shop floor, and now we want to verify that that's a good program before we use it again? You don't have to have operations generating the G-code. You can take any G-code file and simulate it, and the control panel looks exactly like it does right now. So this might also be useful if you've got a program from another CAM system that you were using previously, or just an archive, a program that you haven't run for a while, and you know it's a good program, but your operators need to see how that program is going to run before they feel confident to go out and actually make the parts. Those are all reasons where you might want to simulate an existing G-code file. Now there's also an Analyze button here that allows us to take measurements, and in fact you can stop the simulation at any point and use the Analyze tools to measure distances, say from the head of the machine down to a fixture or something like that. And this is a huge advantage of the simulation in NX. Our competitors create STL files of all of their machine tool components. In NX, the machine tool components are assemblies. They are just regular CAD part models that we're moving around. Okay, let's continue here. I'm going to close this particular file, and we're going to move on to our next file. We'd like to continue and look at some of the other options that are available. I didn't really go into the options form in the back of the simulation control panel. So here we'll demonstrate some of that by looking at a situation where we need to do some collision checking. Here again it's telling me I've got a spindle speed of 0 on one of my operations. And before I begin, I want to go into simulation settings, and let's talk briefly about some of the other options that are available to you. We've had an Earth stationary mode, and that's really the one I prefer, but you can do a tool stationary mode where it looks like you're on a camera that's riding along on the head, or you can do part stationary. Again, in this case, the machine tool base is always stationary and we move around it. Then we can also apply a length increment to the timing when NX creates the Boolean removal of the operation as you move through it. And the reason for this is if you make this length increment really short, you get a very accurate looking simulation, but of course it requires more resources on your processor. So by making this longer, if you've got a really large part, you can speed through that simulation much more quickly. Also, we can then save our in-process workpiece as a part file when we're done. You might use this for other operations or for checking later. What we want to look at now, though, are the options that are available with collision detection. And in this case, I'll remove this pair, and I'm going to create another pair. You can have as many pairs for collision detection as possible. And sometimes people ask, well, why not just check everything against everything? And while you could do that, that could really be a drain on your resources. So generally, you're going to pick pairs of things that you're actually interested in checking for collisions on. So here I'll say I want to check by class, and my class is going to be any tool. And here I'll just select components, and I'll say I want to pick these clamp components. And we'll look at a collision clearance of 40 thousandths, which is pretty small. So it'll, in some cases, warn us then when we've gotten within this range before a collision actually takes place. So let's go back to the simulation control panel. I'll turn on the toolpath so we can see what we'll be doing, and let's hit the play button. So here we're rotating our head into position, and I will show you one other option here. We kind of went through this earlier, the machine axis positions. If we do violate the travel limits of any axes, it'll turn red here to let us know what the problem is. Again, this is very useful to let you know how much of your travel you're actually using. Okay, so I've got that tool pulled back pretty far to start the hole. And in this case, that was successful. Now, let's look at it again. And I'm going to go back into the tool side and make that tool a lot shorter. I'll regenerate. And simulate. Now I will go back and check those options, but I think you'll see that it actually remembers the pairs, so you don't have to reset them every time. Oh, wait a minute. I think I changed my geometry here somehow. I did. Well, I seem to have created a problem with my avoidance here. Okay, let's try this one then. So here we have a much shorter tool, and it's telling us immediately that there's going to be a collision. So specifically it states that it's interfering with the fixture elements that we've set, and you can see them here purple because it's a clearance violation. It's within that 40 thousandths, and then we continue, and it'll continue to hit that clearance violation every time we get close to those fixture elements. Okay, let's move on to our next file now. And here we'll look at the use of the dynamic tool axis. Before I begin, I'm going to hide some of the parts in our machine tool, make it easier to see. Again, these are just assemblies, so I can come in here and hide the sheet metal housing around our machine tool. We'll begin this demo not at the simulation side, but we're going to go and look at the operation itself. One of the primary advantages of NX simulation is its ability to actually integrate and work within the NX CAM environment. So here in the operation then, this particular cut that I'm doing is using an interpolated vector. If I hit the edit button here, you see that immediately we're brought in with the machine axis positions, and we are looking at individual vectors on this cut that we're about to perform. So if I grab any one of these rotations and start moving this vector, you'll see that NX has linked in the movement of the machine tool. As I move the axis down, you see that the Z-axis turns orange because it's run out of travel, and that's indicated over here in the machine axis positions. So I need to move this back up again until it's a valid position for the machine tool. What's the advantage here? The advantage is that as a programmer, you'd like to get these mistakes solved as quickly as possible. And while it's great to catch them in the G-code, we'd rather fix the mistakes while we're doing our programming work. So here we can see collisions, travel problems, and get them resolved before we even generate the code. So that ability then to use dynamic tool axis positioning is very valuable and an important part of the NX CAM simulation. Now we'll move on to our last file. And this is a twin turret machine tool. So this is still the standard IS&V. It's a little bit of a different application because now we need the ability to synchronize twin turrets. So these operations here are assigned via the tools to one turret or the other. Let me just show you how this is set up because this is really the important part of this. If we look here at the lower spindle, you see I've got some various pockets. So let's look at pocket 4. Here's an axial tool holder with a single tool in it. But you can also have some of the pockets here, I think, actually have here's a duo turn. And so there's pocket 1 and pocket 2. And here's the 2 tools that are in here. You can see them clearly. And if we slide this thing around to a different position in here, you're actually going to see it move out in the graphics window. So the graphics are automatically generated by the decisions you make here and are always kept associative. Now, it's a pretty extensive program. We won't take the time to run through the whole thing, but I do want to show you how we can apply some of these other features of our IS&V to complex situations like this. So let's begin. Back at the program view. I'll simulate starting just as I did before, but now it prompts me to enter the synchronized environment because it recognizes that this is a synchronized toolpath. Okay, so a little different interface, but I think you probably recognize some of what's here. For instance, the Show 3D Material Removal button just highlights the stock for us, and then we've got simulation settings just like we did before. Here in this lower pane, you see not one G-code window, but 2 G-code windows, one for each channel. And this represents what we need to send to the machine tool. Each channel is going to have its own program, and the machine tool uses weight codes to determine which channel is going to run, and you see those appearing here, so it's going to match up weight codes to make sure that we don't have any crashes on the machine tool. Down below we've got a time chart that shows the entire program with areas where the weight codes are, dead areas showing where no spindle is running, and this, no tool is running in one of the channels, and this can really help you to optimize as you're moving tools from one channel to the other to try and reduce your cycle time. Okay, let's hit the play button. I just want to show you one tool and what the very beginning of this program looks like, where we're actually doing a part pull-out. So we're using the subspindle to do the pull. It's moving forward. You can see the jaws clamp. We unclamp here, pull the stock out, and then the jaws reclamp. So a very accurate simulation of what's actually going to take place here. Now we're doing, again, a kinematically accurate tool change. The cycle time is correct. I'm moving into position. And I'll just kind of window in so you can see. And we'll speed this up a little bit. Okay, So that's our first operation, and then we continue from there, going through the weight states and the various other tools. At this point, I want to turn it back over to Sarah to conclude our demonstration today.
Thank you, Andy. So that concludes our presentation of NX IS&V. I hope you found it informative. We will open up the lines in a few moments for Q&A, but before we do that, I want to tell you about our 3 upcoming sessions. On April 1st, we will be showing you how NX Integrated CAD/CAM can deal with last-minute change requests from your customer. We'll also talk about how you can quickly design a fixture library and also how to heal STL files for machining rather than having to recreate your parts from scratch. On April 15th, we'll talk about NX on-machine probing to automate the process of programming your Run-A-Shop probes. And finally, on April 29th, we'll end our series with a presentation of NX CMM, which can help to alleviate the bottlenecks you might be experiencing in your inspection departments. If you want to talk to us before the upcoming sessions, our contact information is here on this screen. And you can visit us anytime at our website at acuityinc.com, and be sure to check out our new blog, which we just started about a month ago, at acuityinc.com/blog. Thanks so much, everybody, and I will open up the lines now. Have a great day.